All right, so chapter 9, this is a very interesting chapter. It basically talks about three different things, and these are all theories of how molecules look and how we can approximate what they look like. So let's go to the next slide. So the three different theories that we're going to examine in this chapter would be VSEPR and then valence bond theory, and we'll spend most of our time on those two. And then we'll talk briefly about MO theory, molecular orbital theory at the end. So I'll try to keep this, so this is going to be very abridged. So what I'm going to present in this slideshow, first of all, I'm going to try to keep it under an hour and 15 minutes, even though there's an enormous amount of information in here. So I would probably typically talk about this for longer, but I'm just going to go through the things that you really need to know. So what you'll have to do is go through the slides on your own. The ones that are listed in Canvas, the regular PowerPoint slides, are a lot more inclusive than this. So, for example, there would be concept checks that I'm not going to go through, and reviews and that kind of thing. And I really recommend, if you have time, that you do those also, and do them on your own. And if you can't do them, just email. But so what we're going to do is we're just going to go through the basics, what you really need to know. So we'll start with the VSEPR model. That's valence shell electron pair repulsion, and all it's doing is, you already know this if you were listening to my lecture for 1111, it just means that you're taking the number of things around the central atom in a molecule, and you're arranging them so that they can get as far apart as possible. The reason you need to do that is because they're all electrically charged, and they're all negatively charged, the electrons, so they repel each other. Okay, so that would include atoms, right? Because atoms have electrons around them, or what are called lone pairs, which are just two electrons that are just sticking out by themselves. So either of those could be considered what we're going to call a charge cloud. So you'll have to try to remember this terminology so you don't get all confused, because it's not hard once you see what's going on here. You're just trying to separate these things out as far as you can. All right, let's go to the next slide. So first we'll talk about the VSEPR model. And again, that's where you're just saying, okay, well, we've got three charge clouds around the central atom here. So what we want to do is see how we can get them as far apart as possible. And so let's go ahead and go to the next slide. So this is just a summary of the three different theories. VSEPR, you try to figure out the geometry, as we just said. We'll go on and do that now. Valence bond theory we'll talk about next. It's different because you're talking about the bonds and how the bonds form, and you break everything down into sigma bonds and pi bonds. So we'll talk about that next. And then molecular orbital theory is a very fascinating thing, and it seems complicated. And I think a lot of times people in this class just kind of feel like they just can't do it. And actually, it's the easiest of all of these to do. Excuse me. So we'll see why that's true when we get to that. Next slide. So it says here, MO theory is more powerful, which is true, but all of these different models, including what we did last chapter with the Lewis dot structures, they all have a place. So when you're doing these kinds of structures, usually what you would have done previously would have been to do the Lewis dot structures. And then you would start off and do one of these or all of these. They all have their high points. Next slide. All right, so VSEPR, what we want to do is for each molecule, we want to see how many, what we're going to call charge clouds, you see that in the third line there, are around the central atom. Now, it isn't that we don't care about the central atom, but it's just that we want to know how many things are around it for this particular purpose. So again, a charge cloud can be one of either two things. It can either be an atom or a lone pair. Okay, the charge clouds will always be the same, which you'll understand this better when we get to some examples. But like, for example, water and ammonia and methane. Okay, they all have the same, what we call electronic geometry, because they all have 4 charged clouds around them, all 3 of them. So they're all going to have the same, what we're going to call, and you'll have to remember this, electronic geometry. But they won't have what we call the molecular shape the same. So water's shape, if you just look at the atoms of it, will be different from ammonia, which will be different from methane. So at the bottom it says there's a difference between what we're going to call the electronic geometry, which would include not only the atoms but also lone pair electrons. And then there's also the molecular shape, and that would only include the atoms. Okay, so let's go to the next slide. All right, so for 2 charged clouds, they're always going to be the same. So both the electronic geometry and the molecular shape are going to be linear. The reason being is that because if you have a central atom like that black sphere surrounded by 2 other things, then the way they can get as far apart as possible is to just orient themselves in a straight line, as they're doing in both of these. So for both CO2 and also for HCN. Notice that, I mean, we'll come back to this later when we talk about valence bond theory, but notice that in both of these molecules, that carbon in the middle has a total of 4 bonds around it. So 2 of those are going to be bonds that are directly between it and the thing it's bonding to. And then 2 of them will not be directly, so we'll talk about that later. But so there's really nothing that changes on this one. So for 2 charged clouds, all you have to remember is one thing, and that is that the shape is linear for both the molecular shape and also the electronic geometry. Now it's going to get more complicated when we get to 3, and 4 and 5 and 6, and that's because when we get to those, we'll find that we can actually replace one of the atoms with a lone pair. And if we do that, then, well, the electronic geometry won't change, but the atomic shape will, the molecular shape. So let's go to 3. Next slide. All right, excuse me. This is a summary of everything we're going to talk about, and it's only showing here the molecular shapes on the far right column. So everything from where it says example at the far right all the way down, those are all molecular shapes. So none of these things are going to be talking about electronic geometry here. In the center column, those things that you're seeing there around the A thing all the way up and down, the A thing is the central atom, and then you start with 2 things around it and then come down a road to 3, 4, 5, and 6. And so those things that you see, those things that are shaped like clouds or like, I'm not sure what you would even describe it as, but those that kind of like gray things, those like kind of like cones that are coming off, or things that could be called charged clouds. They could be either atoms or they could be lone pairs. So over on the right hand side, they're only showing the atoms. So this will be the same as far as the electronic geometry and the molecular shape for all of those. So we've got 2 at the top and then 3, 4, 5, 6. And thankfully that's all there is. So for all of those, if they are like that, the way you see them, which we'll go through that in just a second and look at the shapes, then that means that for all of those, the molecular shape and the electronic geometry will be the same. The reason is because everything is an atom. So nothing has been replaced by a lone pair, and you'll probably see this better as we go along. So at the top there, we have 2 charged clouds, and we've already discussed this. The way that they can get as far apart as possible is to orient themselves in a straight line. Just below that, we have a yellow sphere with 3 red balls around it. That's 3 charged clouds around a central atom, and the way they can get farthest apart is to arrange themselves in a plane, so it's all in one plane, and they're at 120 degrees from each other. And if you'll look back to the left under 3, it says that's called, and you'll have to remember these names, it's called trigonal planar. Now these names are not going to be on your formula sheet, so you just have to memorize them, but they kind of make sense because, like for example for this one, It's all in one plane, which is where the planar comes from, and then the trigonal means there's three things there. Okay, come down to 4. This one you have to just memorize. It's called tetrahedral, and it turns out that's the way that 4 things can get as far apart as possible, by arranging themselves in what's called the shape of a tetrahedron, which you probably never heard of before, but it looks kind of like a pyramid, but not exactly. So if you look there, you've got a black sphere with 4 whites around it, and the one white thing is sticking straight up, and the other 3 white things are kind of like a spaceship pod or something like that that would land on something. So you have a total of 4 things around a central atom, and so this is called tetrahedral. Come down to 5. You have now 5 things around a central atom. Now remember, we're not including the central atom when we count to 5, right? So the central atom is out. So you have 5 green spheres there around a central, kind of a gray one or silver. All right, so the way they can get as far apart as possible, one goes to the top, one goes to the bottom, and then the other 3 make themselves just like the trigonal planar thing above, where they're 120 degrees apart in one plane. And then come down to 6. The way that they can get as far apart as possible is kind of like 5, except you have 1 on the top, 1 on the bottom, and then 4 around the middle. All right, so if you go back and start back at the top at 2, we're not going to really do anything more with that. So you can forget that. It's always going to be linear. But once you come down to 3 and then 4, 5, and 6, for all of those, there's a way that we can take away one of the atoms and replace it with a lone pair. So for example, in 3, we could pull off one of those red balls and say, hey, we're going to put a lone pair of electrons here. So, or for 4 or 5 or 6. Now for 4, you can actually take away 1 or 2 and replace 2 with lone pairs. And for 5, you can actually take off 1 or 2 or 3 atoms and replace them with lone pairs. So when you do that, you're not changing and this is so important, you're not changing the electronic geometry, because you still have something there. It's just that instead of having an atom there, you have a lone pair of electrons. But it does change the molecular shape, because you only look at the atoms for the molecular shape, and we'll see this more as we go through these. And then also for 6 there, you can take away either the top one or the bottom one. And so let me just say something right now, and I'll probably repeat it later. For 5, for trigonal bipyramidal, and I forgot to mention that the name for that 5 thing is called trigonal bipyramidal, and that's because there's a pyramid pointing up and a pyramid pointing down, and both of them have the same 3 things for their bases. So because there are 3 things at the base, that's the trigonal part. The pyramidal is because there's a pyramid, but the bi comes in because there are actually 2 pyramids. For 6, you could call that, actually you could call that trigonal square bipyramidal for 6, but they don't. They call that one octahedral. So back to what I was going to say. If you look at 5, whenever you start, like if they tell you you're going to replace an atom with a lone pair on 5, then you have to remember this. You take away from the ones that are around the middle there, the 3 that are in one plane around the middle. For 6, you take off the top one and then the bottom one, and leave the ones that are around the middle alone. And if you can't remember that, you'll get totally confused. So it does matter how you remove them. So again, for 5, you leave the top one alone and you leave the bottom one alone. And if you don't know what I'm talking about, you'll see it in just a few minutes. And you remove from around the middle. For 6, you leave the ones around the middle alone and remove the top one and the bottom one. Next slide. All right, so for 3 charged clouds, we have trigonal planar, and that's for both electronic geometry and also molecular shape in the top one there. So, and the reason is because there's an atom in all 3 locations. Now come to the bottom, and you see that for the thing at the bottom there, which is SO2, we have removed one of those atoms and replaced it with a lone pair, as you see at the left. So at the left, you see the Lewis dot structure, and there's a lone pair there sticking out to the left in green. You still have the O's, the two O's and the S. So the electronic geometry won't have changed. It's still trigonoplanar because you still have three charge clouds in one plane. But notice the molecular shape now is no longer trigonoplanar. Why? Because we lost the atom that was sticking out where there's now a lone pair. So what we do is we say that that shape is called bent, B-E-N-T, bent. And it's because it's just like if you take a piece of wire and bend it, right? So that's the shape for SO2. It's also the shape for H2O, which we'll see later. All right, so the two things for three charge clouds, it can either be trigonoplanar, the molecular shape can either be trigonoplanar or it can be bent. And that's all you have to remember for three. So as we go from 3 to 4 to 5 to 6, there will be other possibilities. But the electronic geometry for 3 is always trigonoplanar, the electronic geometry. Okay, next slide. For 4 charge clouds, and again, remember I've abridged this quite a bit, so I'm skipping a whole bunch of slides through here. For 4 charge clouds, the electronic geometry will always be tetrahedral, always. But the molecular shape can change because you can take off, and in this case it doesn't matter which one you take off, so you can take off either 1 or 2 of those atoms, replace them with lone pairs, and you'll have a different molecular shape, right? But you'll still have the same electronic geometry. So let's go to the next slide. So starting at the top, we have methane, and it has electronic geometry that's tetrahedral, and also the molecular shape is tetrahedral because everything is an atom. But if you come down to the next row, we've taken one of the atoms off, one of the H's, replaced it with a lone pair, as you can see on the left there. So now we still have an electronic geometry of tetrahedral, but the molecular shape's not tetrahedral anymore, right? It's a little pyramid with 3 things at the base. So we call it pyramidal. Excuse me, and we call it trigonopyramidal because there's 3 things at the base. So that shape there at the right with the blue sphere and 3 white spheres under it is called trigonopyramidal. Okay, so that's the molecular shape. And then at the bottom we've got water with an oxygen, which is red, and 2 white hydrogens. So there we've replaced 2 atoms with lone pairs. So still for water, we still have a tetrahedral electronic geometry, but the molecular shape is no longer tetrahedral, right? It doesn't look like the thing at the top anymore. So what does it look like? Well, it looks like the thing we call bent, B-E-N-T, bent. So let's just review very quickly. For all 3 of these, the electronic geometry is tetrahedral. And if you look to the left there, you can see all of these have 4 things around the central atom. I'm talking about the Lewis structures. Again, you would typically draw the Lewis structures before you do any of this. Or you don't have to necessarily draw them. If you want, you can look them up online. But typically, on the exams, you'll be given something like CH4. And the first thing you'll have to do before you do this, and this is one of the tricky parts, is you have to figure out what's the Lewis structure. So you can't really practice too much drawing the Lewis dot structures. The more you practice, the better off you'll be on the test. And also, the more you practice, you'll actually start to remember some of them. Some of the more difficult ones, you will remember how it worked. So this is one, anyway. All right, so on the right, the right-hand column, going from top to bottom, we've got tetrahedral for the molecular shape. Second row is going to be trigonopyramidal, and bottom row is bent. And so try to remember those words. Next slide. Okay, for 5 charge clouds, the electronic geometry is always going to be trigonopyramidal. Trigonopyramidal. You have 2 pyramids. One points up to the red sphere at the top, and one points down to the red sphere at the bottom. Let's go now to the next slide. So this one is the one that has the most possibilities. Remember to remove around the middle. So if you look at the top right, when you have SF4 there, the S is yellow and then the F's are kind of a pale green. For that one, for SF4 at the top right, we've removed an atom and we've replaced it with a lone pair. So the electronic geometry won't have changed, and I'll probably stop saying this over and over again, but the electronic geometry will still be trigonobipyramidal, but the molecular shape is not like the molecular shape at the left. Can you see the difference there? It doesn't look like a trigonobipyramid anymore. It looks like a seesaw. So that's what they call it. Very scientific name there. So that is called seesaw. If you remove another one of the atoms around the middle and replace it with a lone pair, like at the bottom left of the slide, like the thing that has the Cl in the middle with the 3 F's, then you now have something that looks like a T. Okay, so they call it a T shape. And then if you remove that last thing that was around the middle, the thing that's in the T shape, the thing that's sticking out to the right, and replace it with a lone pair, again, I mean, hopefully this will be the last time I'll say this, but the electronic geometry is still going to be trigonobipyramidal. But the shape of that molecule over to the right with those 3 kind of like purple colored spheres is linear, right? And that looks just like what we saw at the very beginning. Next slide. And then the last possibility is if we have 6. So if we have 6 atoms around a central atom, which is what we see at the top left there, then the shape and the electronic geometry are both octahedral. So octahedral, if you look all the way to the left where there's a figure that's kind of like a light red color or orangish red, you look at that and you see that it has 8 faces. That's why it's called an octahedron. An octahedron is something that has 8 faces. Okay. Now remember for this one, when you start to take off the atoms and replace them with lone pairs to see what the shapes would be, you do it at the top and the bottom, not around the middle. So for the one that we're looking at here, the shape would be octahedral. Let's go to the next slide. If we remove, for example, the one on the bottom and replace it with a lone pair, now we have a shape that looks like a pyramid with a square base. There are 4 things at the base, so it's called square pyramidal. One thing I forgot to mention, I was going to say it in the previous slide, but I'd already indicated that we should go on, is that if you look at SB there in the middle, or come down to xenon in the one on the bottom here, count the number of electrons that are around it. Well, for the SB there, the antimony, it's 2, 4, 6, 8, 10, 12 electrons. Okay, so, but we said, right, that typically atoms in the main group will not take more than 8 because of the octet rule. But then remember, we said, oh, but there's an exception for that, right? So once you get to the 3rd row, which has the S and the P, and below, the main group elements can take either 10 or 12. The reason is because they now have more suborbitals available to them, so, and they're bigger, so they can accommodate more electrons. So it's okay for things to have either 10 or 12 electrons around the central atom in the 3rd row and below. Okay, so anyway, if we remove the one on the bottom and replace it, now we have square pyramidal. And then if we also remove the one on the top, then as we see at the bottom here, xenon F4, we have a shape that looks like a square plane. This is like the trigonoplanar we saw before, but it's not trigonal, it's square. It has 4 things around the central atom. Okay, and that's it. So if you got most of this, then you're done, and all you have to do is just go back over them a few times and make sure that you understand that. And that's basically what we need to know for the VSEPR model. And what we're going to also do, and it was also done in the lab if you happen to be in 1111, the lab that I just gave for the one that we're going to do Wednesday, 2 days from now, That one, what I did was I also tied this in with the thing that we're going to talk about next, which is valence bond theory. So we'll do that also here. So uh, we'll get to that in just a few minutes. All right. So basically, this is what you'll need to know. So what they'll typically ask you to do is to take a formula like if you look at the bottom left of this slide, it says XeF4, that's xenon tetrafluoride, right? They'll give you that formula only, and then they'll ask you what kind of a shape would it have. So what you have to do, it's absolutely imperative, before you start trying to figure it out, like, because if they just give you that, like XeF4, and you just look at it, you're going to think, okay, there's 4 things around a central atom, so it's tetrahedral. But you'd get it wrong, and that happens every semester, and it'll happen this semester and next. The reason is because you can't do it that way. You first of all have to very quickly take a piece of scratch paper, which is one of the reasons why I don't use a lockdown browser in exams, is because if you look away, then it can lock you down, and you have to look away to be able to do this. So anyway, you would have to first of all take a piece of paper and very quickly sketch the Lewis dot structure. Okay, so how would you do that for xenon F4? Well, xenon is 8 electrons. It's all the way over in the 8th column. Fluorine is in the 7th column. It has 7 electrons in its valence shell. 4 times 7 is 28, plus 8 is 36. Then when you draw that little structure on the right, you use 8 of those, but that leaves 28 electrons that you haven't used. You can put 6 on each of those 4 fluorines, and that would use 24, but you're still left over with 4. And they have to therefore go on the xenon. So if you do it right, and if you draw the Lewis dot structure, then you end up with a xenon having 2 lone pairs. That's those 4 extra electrons, and then also having 4 bonds to the F. So you can see there are not 4 things around it, as you would have thought if you just glanced at it. There are 6. So the electronic geometry would be octahedral, but the molecular shape, so it depends on which one they ask, but the molecular shape would be square planar. Now it's going to be the same thing for the thing above there, the SbCl5. If you just glance at it and say, okay, 5 things around a central atom, it's got to be trigonal bipyramidal, and you'd get it wrong. So it's worth taking just a few seconds and just quickly sketch out your Lewis dot structure before you do these. All right, let's go to the next slide. So I'm not going to do all of these. This is one of the concept checks that I retained. I'm not going to do HCM because it's not particularly interesting. And I think we did it before. But we'll do the pH3 real quick. So what you'd want to do for pH3 is sketch the Lewis dot structure. So 5 for the P, 3 for the H's, that's 8. You would have a P in the middle with 3 H's around it. So you'd use 6 of those, and that leaves 2 to go on the P in the middle, which means that pH3 is going to have a tetrahedral, because it's got 4 things around it. It's going to have a tetrahedral electronic geometry. Okay, but it won't have a tetrahedral molecular shape, but we'll see that in just a minute. It's going to have a trigonal pyramidal shape. And then for the SF4, you would just do the same thing. So let's go to the next slide. So here is the pH3. You can see on the left, that's the Lewis structure. You have 4 things around a central atom. You have to get that first so you can see what the basic electronic shape is, the electronic geometry. You can't do the next step until you do that one, or you'll just miss it most of the time, if not always. Okay, so you can see there on the right-hand side that the shape of the molecule is trigonal pyramidal, right? So it doesn't look like the thing on the left. Next slide. I'm having a hard time getting this thing to change. Okay, for the SF4, you would do the Lewis dot structure, which is done at the bottom left, but you would have to do this yourself. So count up your valence electrons, put the S in the middle, put the 4 F's around it, and then see how many electrons you used, and then put 6 electrons on each of the F's, and you'll find that there are going to still be 2 electrons left over, and so there's only one place left to put it, and that's on the S. So that means instead of having 4 things around the S, you have 5. You have the 4 F's, but you've also got a lone pair. So what's the electronic geometry for that SF4? Well, 5 things right around the central atom means you've got trigonal bipyramidal. But the molecular shape is not trigonal bipyramidal, it's what? So do you recognize that shape? It's a seesaw shape, right? So they're different here. And this is exactly the kind of thing that they ask on the final and that I'll ask on my exam. Excuse me. This house I live in is just loaded with allergens. Okay, let's see. Okay, so let's go to the next slide. Wow, I'm having a really hard time getting this thing to switch. I don't know if it wants me to stay on that other slide longer or what, but it shouldn't be. Okay, so here are a couple of other ones, which I'm not going to go through all of this. I'm just going to point out, once we've done the Lewis dot structures, what the shapes are going to be. So for O3, you have 3 charge clouds, so the electronic geometry would be trigonal planar, but the molecular shape is bent because you don't have an atom in all those locations. For the KRF4 at the bottom, your shape there, as you can clearly see, is square planar. It's a plane with 4 things around it, so it's square planar. But that is not the electronic geometry. The electronic geometry would be octahedral because you've got a lone pair above and below. And let's also look at the next slide. Wow, I had to click that thing like 5 times to get it to move. Okay, so this is what it would actually look like. I'm not sure if this is exactly the same molecule, but it's the same deal. So you've got 4 things around a central atom, and you've got a lone pair on the top and the bottom. Okay, so I think you're getting the idea. All right, so let's go to the next slide. All right, let's talk for just a moment about dipole moments. So remember back to the previous chapter, we talked about electronegativity. So when you have something like water, a molecule like water, it will be polar because the oxygen is much more electronegative than the hydrogen. So that means it pulls more of the electrons to itself. That does not mean that the O has a negative charge, but it just has more electronic density than the H's do. So the way that we describe that is we say that the O has a partial negative charge, and that's represented by that lowercase Greek letter delta with a minus sign. The H's are a lowercase Greek letter delta plus. That indicates that they're partially plus. Well, when you have something like that, it's called a dipole, and I don't want to take time right now to discuss what a dipole is. So you can look it up online if you want, or I mean, also if you had physics, you already know. But it's just something like what we have here. So when we have something like that, we have a dipole moment between the O and the H on the top, and another one between the O and the H on the bottom. So both of those bonds are polar bonds. And the molecule H2O is also, overall, it's also polar because the 2 polar bonds don't cancel each other out. What that means is, like, if you took one of those H's and moved it around on the opposite side of the O from the other H, then yeah, you would have 2 polar bonds, but because they're pointing in opposite directions, they would cancel each other. That's what it means here, but they don't. And the reason they don't is because that's the way it would actually look in nature. Remember that O also has 2 lone pairs on it, and they're going to be sticking out in the other 2. areas of that tetrahedron. So they'll force those H's to be exactly the way they are. So what happens is that the net molecule or molecular dipole moment will be the vector sum, and you don't need to know this, of the two bond dipole moments. So the way you do that is you just do it in vector. You do vector addition where you're using the cosine of the angles, which you don't need to worry about that. And so you wind up with something that does have a net dipole moment. Next slide. Wow, it worked the first time. Okay, now notice here that CO2 is the same way as H2O, almost. So for CO2, you've got two bonds that are both polar. Again, because the O is more electronegative than the C. So the bond that goes from the C to the O on the right is polar, and it's going to be partially negative for the O. And also the bond that is to the O on the left, it's also polar. But in this case, they're pointing in opposite directions, so they cancel each other. So CO2 as a whole doesn't have a dipole moment. It's neutral. Next slide. So a little concept check, one that I left in. True or false, a molecule that has polar bonds will always be polar overall. Well, that's the same thing we just talked about with CO2. CO2 has two polar bonds, right? We just saw that. But is it polar overall? No. Why? Because the two polar bonds cancel each other. Next slide. So it's false because CO2 has two polar bonds, but they cancel each other. Next slide. Okay, valence bond theory is the next thing we need to talk about. It's the second of the three main things. And all it's doing is it's trying to take every bond in a molecule and say it's either going to be a sigma bond or a pi bond. Okay, so let's just right up front, what's the difference between them? A sigma bond is like if you have two atoms, it would be a bond that goes directly between the two atoms, or basically it would be between the two nuclei. So you probably were thinking to yourself all this time that all the bonds would have to be directly between the two nuclei, right? And like, for example, the double bond, they would both be between the two nuclei in a straight line. And the answer is no, because you can't have more than one straight line between 2 points. So for each molecule, you're limited to one sigma bond. So you can, between two things. So, I mean, if you have a molecule with 3 things in it, you can have 2 sigma bonds. You can have one sigma bond between the thing in the middle and the thing on the left, and then vice versa. But between the same 2 things, you can only have one sigma bond. So if you had a double bond, for example, between a carbon and an oxygen, how would that work? Because you can't get the second bond there. So what you have to do for the second bond is you have to make it go above and below the first bond. So the first bond is a straight line between the 2 things like the C and the O. And then the second bond goes above and below it. And that's called a pi bond. So the whole point of valence bond theory is to divide the bonds into sigma bonds or pi bonds. So for example, if you have a single bond, then that's just going to be a sigma bond. But if you have a double bond, you have a sigma bond and then you have a pi bond, and that would be above and below it. And then if you have a triple bond, you would have a sigma bond in the middle, and then you have a pi bond above and below, and a second pi bond going around it to the left and the right. Let's go to the next slide. Seems to be working better now. All right, so it was developed for quantum mechanics. Let's go to the next slide. And let's go to the next slide because we've already talked about this. The one thing you might want to look at if you have time, sigma bonds can be formed in all kinds of different ways. So basically, they can come from either 2 s orbitals or 2 p orbitals, or from what we're going to talk about in just a minute, hybrid orbitals. But pi bonds always, I'm at the 3rd paragraph, have to come from 2 p orbitals. Try not to let this confuse you. So if you feel like you're getting confused, then just take what you can for right now, and then just go over it and over it a few times, and you'll start to get it, because it's not that bad. Next slide. Okay, so here's a picture of a sigma bond. At the top here, you've got the two H's with their S electrons. And so they come together to make an HH molecule, an H2 molecule, and the electronic density is centered between the two H's. That's a sigma bond. And by the way, the sigma comes from the S. So in the atom, they're called S orbitals or suborbitals. But in the molecule, we change it to sigma, which is the Greek for S, to show that it's not the same thing as the S. So when you see one S or two S, it's in the atom. When you see sigma, it's in a molecule. And notice here at the bottom now for F2, we're also going to make a sigma bond, but we're using p electrons. And that's okay. As we talked about in the previous slide, you can do that. So it just looks different, but it's the same basic idea. So one of the p orbitals, remember there are three of them, one of them will always point towards the other atom. And so here you can see that for both F's, the p orbital that we're picking here, which we can call the 2px if you want to, but remember there are two other ones, which I'll mention more in just a second. The 2px, let's call that, for both of them, are pointing right at the other F, both of them, in different directions. So when they come together, they just overlap. That electron in that orbital overlaps with the one in the equivalent orbital on the other F. And that's a sigma bond also, even though it's coming from a p electron in the atom. So if you look at the F there, let's take the F all the way to the left. It's only showing one of the three p electrons, but remember that there's also going to be one pointing up and down and one pointing in and out of the plane of your screen. Okay, next slide. All right, so I'm going to kind of like go through this very quickly. They want us to draw methane, so let's go to the next slide. Okay, so here it is. And so we can just look at this, and I'm not really concerned right now about trying to go back through VSEPR or the angles here. The angles would be 109.5, but what we are concerned about here is what is going to be the hybridization. So I'm going to go through this for methane, and then after that it will make it easier for you to see the other ones. But it turns out here that we have 4 different bonds that are equivalent. So what I think I want to do is I want to just go through it. So let's go to the next slide. Next slide. Next slide. All right, so here, look at the bottom question. Why can't the bonding orbitals for methane be formed by an overlap of atomic orbitals? And the answer is, remember we said the electronic configuration for carbon would be 2s2, 2p2, right? So if you don't remember that, just go back and review that from one of the previous chapters. So, or you can just look at the periodic chart. Carbon is 2s2, 2p2. It's actually 1s2, 2s2, 2p2. So keep that in mind. We won't usually talk about like the 1s for carbon because it's not the valence shell, but it's still there, remember. Okay, so, but the valence shell for carbon is 2s2, 2p2. That won't work though. I mean, I can't back up, but if you have the slides in front of you, if you can back them up, or just look at them, excuse me, you'll see that those 4 bonds are equivalent, and that can't happen if you've got 2 of them are coming from S's and 2 from P's. You should have 2 that are S orbitals, and they should look different from the ones that are from the p orbitals, right? Because they're not the same, but they don't. They all look the same. So how did that happen? So let's go to the next slide. Next. 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 And let's go ahead. Okay, so what they're saying here is that what we have to do to get all 4 of those things the same, we have to do what's called hybridization. And again, this is not confusing. It's just like if you take 2 different fruit trees and hybridize them, you get something in the middle. And so we're doing the same thing here. We're taking something from the s orbitals and some things from the p orbitals, and we're mixing them so that the finished product won't be s or p. It'll look kind of like s and kind of like p, but it won't be either one. It's a hybrid orbital. And there are basically, let's see, 5 different kinds of, let me count them up real quick. There are 5. Okay, so, and I'm not going to mention them right now because it'll just confuse you. So there are 5 different kinds of hybrid orbitals, and so let's take them one at a time. So next slide. All right, so the first one, and don't let this notation confuse you, is called sp3. That's the kind of hybridization that methane, CH4, would have. Now look at that sp3 thing, and let's make it simple. If you consider that S to be S1P3 instead of sp3, where they just left out the 1, if you add that 1 above the S to the 3 above the P, you get 4. And that means that this is what would correspond when you have 4 charge clouds around a central atom. So it could work either for water or for ammonia or for methane. Okay, so let's see how it forms. Let's start from the beginning. Next slide. All right, so here we are at the very beginning of this thing where the carbon is still an atom and it's just in its ground state. So again, we've got 1s1, 1s2, 2s1, 2s2, and then we have 2p1 and 2p2, and they have to go in separate orbitals there because of Hund's rule. So we don't really care about the 1s, so just forget about it. We care about the 2 and the 2s and the 2 and the 2p. We have to somehow mix those 4 things together to make them all the same. So what we can do, and it isn't that it's going to happen the way I'm going to say in nature, it doesn't. But just so that we can kind of get an idea of what's going on, just imagine in your mind that we take one of those red arrows like the one that's pointing down and put it up in that empty 2p orbital, the one at the right. So just mentally move that 1 electron over to that empty 2p orbital, and now you should have 1 electron or 1 arrow in the 2s, 1 in the 2p at the left, 1 in the 2p in the middle, and 1 in the 2p at the right. But we still don't have 4 equivalent orbitals, right? We have 3 at the top and 1 at the bottom. So let's take the 1 at the bottom and move it up just a little bit in energy, and take the 3 at the top and bring them down a substantial amount of energy until they're all at the same energy. And then we'll have 4 things that are exactly the same. And that's where the 4 comes from in the sp3. We have 4 things that are hybridized. 1 s thing and 3 p things are hybridized. So 1 plus 3 is 4, so we're going to have 4 charge clouds that can orient themselves around this. So this would be the thing that would correspond to tetrahedral electronic geometry. Okay, so let's look at this in picture form here. So next slide. So here on the right, you can see that we've taken one of the s electrons and moved it into that empty orbital under 2p, or beside 2p there. So next slide. And so next slide. Now on this slide, what they've done is they've moved the 2s thing up a little bit and brought the 2p thing down a little bit, so they kind of meet. If you look closely, you can see that those 4 blue lines for over on the right hand side are a little bit lower than the green 2p lines at the left. And now we have the thing that we need, right? This is what we would need to either make any of water or NH3 or CH4 or anything else that's tetrahedral. Okay, so because it's 4 equivalent orbitals, we call this sp3, where we've taken electrons from 1 s orbital and 3 p orbitals. Okay, so if you can understand this, then you can understand all the rest of this. We're just going to do things a little bit differently So this is one of the 5 things. So we have 4 more to do, and then we'll be done with this. So let's go to the next slide. And then next slide. Excuse me. All right, so this is what these things would actually look like. Over on the right-hand side at the top, if you'll look at that, that is an sp3 hybrid orbital at the top right, the thing with the blue lobe and the red lobe. So it doesn't look like an S, right? Because S's are spherical, and it doesn't really look like a P either, because P's are supposed to look like dumbbells. But which one does it look more like? It looks more like a P, because you've got 3 P orbitals contributing and only 1 S one. So it looks almost like a P orbital that's just been like taken out of shape a little bit. And then the green thing there in the middle is just showing you what it would look like if you had a carbon atom that had hybridized in nature to get ready to make methane by bonding with 4 hydrogens. Next slide. And then at the right, you see what it would look like after the bonds have formed. These are all sigma bonds. All of these are just straight bonds between, for example, the H's and the C. So the green part of that is the 4 hybrid orbitals that the C has formed, and then the H's still have just their basic 1s1 orbital. So, but I mean, they're called 1s1, but then when they make the molecule, as you see here, then we no longer call them 1s, we call them sigma 1s. So the nomenclature is a little confusing, but they're called sigma 1s. Next slide. All right, so now try to hold on for this one. This is the next step, sp2. So look at the sp2. We can rewrite that as s1p2, which 1 plus 2 is 3. So this is going to correspond to our situation when we did VSEPR, when we had 3 charge clouds. Remember that the electronic geometry there was trigonoplanar. So everything that has sp2 hybridization will have trigonoplanar geometry. Next slide. So we want to draw the structure for C2H4. This probably isn't the best example, but let's use it. Next slide. So, well, we haven't got a picture in front of us, but the shape for both of the carbons is going to be the same. And that's one of the reasons why I don't like this example, because you have 2 things here that are both the same. But if you drew this, which we're going to see that in a minute, then you would have a trigonoplanar arrangement around each carbon. So clearly that's different from what we saw with sp3. Next slide. Okay, so here at the bottom right is the picture. So each of those carbons has a trigonoplanar arrangement where, and it's also going to be the molecular shape for each of them in this case, because they're all atoms. So for both of the carbons, you're going to have one plane, and actually it turns out the whole molecule's in one plane, so it's flat. The whole thing is flat. And each of the carbons, which I'd prefer not to use this example, but each of those carbons has 3 things around it. So check that out for yourself. Let's go to the next slide. So clearly sp3 won't work here, because we would have to have 4 things around the carbons for it to be sp3, and we don't. Next slide. And then the angles would be different. Next slide. All right, and then let's go ahead and go to the next slide, because I want you to see this in a diagram form. Next slide. Next slide. Next slide. Okay, so here's where I want to start for this. So notice here, what we're doing again is we're looking at carbon. This is a carbon atom. And so we started out with 2 electrons in 2s, and then 1 in the first 2p and 1 in the second 2p. And then they've already cut to the next step here, or I have, where we've taken one of the electrons out of the 2s orbital and put it up into one of the 2p, the one that was empty before. Okay, now go to the next slide. So we're going to do this kind of like what we did for sp3, but instead of taking all 3 of the 2p's and bringing them down a little bit and bringing the 2s up quite a bit to meet, notice over on the right hand side we're doing it differently this time. We're only taking 2p two of the 2p orbitals and lowering them down, and 2s orbital and raising it up. So that notice here on the right hand side we don't have 4 things that are equivalent, we only have 3. So one of the things is left at the top, the 2p is left and it doesn't change. So you still have that electron in the 2p, and it's just a 2p electron. And then you have 3 things below it that are a hybrid between 1 s orbital and 2p orbitals. So we call that sp2, and that's why you call it sp2. And also, if you add the 1 plus 2 is 3, that means it's going to have 3 things oriented around it, which we just saw, right? Both of those carbons have 3 things around them. So they'll have the 3 things around them, and then on the top and the bottom, you'll have that p orbital still there. Next slide. So this is like basically the picture you want to go to. This is like the best picture I've ever seen for this. So this is the same thing we saw before. It's ethylene, C2H4. So if you look at the carbon atoms are right in the middle of those 2 like messes where you've got things sticking out everywhere. The carbons are right in the middle there. And those like 3 lobes coming off of the carbons, one to the right, one kind of to the top left, one to the top bottom left, would be the 3 sp2 hybrid orbitals. Okay, and then remember we said that there was a p electron that was still a p electron. So it's going to be the thing that's blue and red, the thing that sticks up above the plane of the molecule and below it. So that's that one other electron, and you have the same thing over on the right hand side. So what can happen is that you can make a bond form between those 2 sp2 hybrid orbitals that are pointing right at each other where that larger green arrow is, and that would be a sigma bond. But you can also make a bond between the blue lobes and the red lobes, and that bond would be above and below the first one. So that would be called a pi bond. So this is what a double bond really looks like. It's a sigma bond in the middle with a pi bond above and below. And then the H's can do the same thing we saw before. They can come and make a bond with the hybrid orbitals, 2 on the left and 2 on the right. But that's not really what we're that concerned about right now. So anyway, this is what this would look like as it's coming into shape when you have sp2 hybridization. So remember, whenever you have sp2, 1 plus 2 is 3. You're going to have 3 charge clouds oriented around whatever the central atom is, and that would be those 3 turquoise lobes around each of the carbons. Also remember that whenever you have sp2, it's going to be flat, and also it's going to involve a double bond. So sp3 was all single bonds, sp2 is a double bond, and then we'll find out later there's another possibility. Next slide. And here's another picture of it that's very good. The thing that's on the left there, we just kind of looked at that before. On the right, you can see that they don't show the H's here, but that doesn't really matter. So you can see there that kind of light green thing in the middle. I'm doing the one on the right-hand side. Here you can actually see the bond. The green bond is the sigma bond, and then the red and the blue bonds are 1. It's not 2. It looks like it's 2 bonds, but it's not. That's actually 1 pi bond. So when you have 1 bond that goes above and below, that's considered 1 bond because it's got 2 electrons in it. And we'll talk about more later. Okay, next slide. And then this is the last one we're going to really talk about in detail. So sp, 1 plus 1, we can rewrite that as s1p1. 1 plus 1 is 2. That means you're going to have 2 charge clouds around the central atom. So that's the relation of this back to VSEPR. Next slide. We're going to draw CO2 here. Next slide. Next slide. And next slide. Okay, so I'm having trouble again getting this thing to shift. All right, so we had actually done this one before. So CO2, at the bottom right of this slide, you see the Lewis dot structure, and it is 2 double bonds. So whenever we have this, we're going to have linear shape, a linear shape. So how do we account for this? So before we go to the next slide, let's just realize that this is not the way methane looked, and it's also not the way that ethylene looked, right? It's different. So methane was tetrahedral, ethylene was trigonal, planar, and this is what? It's linear, right? It's all in a line. So we clearly have hybridization here, because it has to be hybridized, because otherwise you'd have 2 going one way and 2 going the other way. But this hybridization is different, so we call this one SP. So S1P1, 1 plus 1 is 2, 2 charge clouds oriented around the central atom. And in this case, it's the 2 O's. Next slide. And so let's go ahead and go to the next slide. And the next. All right, so let's go through it again as we did the other two. So again, we've got 1 2s electron and 3 2p electrons. Next slide. In this case, we do kind of what we did for sp2. First of all, we've already moved the 2s one up. So we have 1 in the 2s and 3 in the 2p, but this time instead of only leaving 1 electron in a 2p orbital, we do it for 2 of the 2p orbitals. So we're going to just bring down that 1 all the way to the left there, which we can call it the 2px if you want. And we're going to hybridize it with the 2s orbital. And so if you look to the right where that gray arrow is, that large gray arrow, we see that we only have 2 hybrids there. So for sp3 we had 4, for sp2 we had 3, and for sp we only have 2. So that means that 2 of the electrons got left up above there in p orbitals. So that means that since each one of those can make its own pi bond, then when you have this kind of hybridization, you can make 2 pi bonds. Next slide. So this is not the best picture in the world, but it's the best one I could find. And it's hard to see what's going on here because of the way they did this. But so look at this C thing in the middle. Those 2 hybrid orbitals are going to be that kind of a greenish color. One's going to the right and one's going to the left, and they're making 2 sigma bonds with the O's. So that's sp hybridization. So notice we've got 2 things around the carbon, the 2 O's. So 2 charge clouds around the central atom means we have a linear shape. And then we've still got 2 electrons on the carbon that were left in the p orbitals. Now that's also true for the O's, but we don't really need to worry about that right now. That's kind of like more advanced. So just worry about the C, the carbon. So one of those p electrons can make a bond up and down, or above and below the plane that's made by that first sigma bond. So that's the one that sticks straight up and straight down. That's one bond. So that would be a double bond, right? Just as we saw before. The sigma bond there between the C and the O on the right would be one of the bonds, and then the bond above and below is one bond that's called a pi bond. That would be the second bond in the double bond, as you see in the Lewis dot structure. And then the same thing on the left, except that in the one on the left, you have to have the pi bond has to go in and out of the plane of the screen. Because if it didn't, if it were trying to go the same direction the one on the right, then they'd just get in each other's way. So they'll move at 90 degrees to each other. All right, so the thing to remember here is when you have sp hybridization, you have a linear shape, 2 charge clouds, S1P1, 1 plus 1 is 2. And you can have like this where you have 2 double bonds. Remember sp2 is 1 double bond, so sp can be 2 double bonds, 2 double bonds. And it can also happen if you have 1 triple bond. Like, for example, carbon monoxide would be sp hybridized. because it's got C triple bond O. And then you've got a lone pair sticking out on the O and the C both, and that would be taking the place of the hybrid orbitals. It isn't taking the place of the hybrid orbitals, it is the hybrid orbital, but it's just that instead of making a bond, it just stays as a lone pair. Okay, so this is what you really, really need to know. So go back through these three a lot because these are really important. So sp3, sp2, and sp, and then we've already indicated how they tie back to VSEPR. Now there are two more hybridizations. We have to have one for 5 charge clouds and one for 6, but I'm not going to spend as much time on these, but I will go through the basics of it. So we've already used up all the S and P orbitals at this point. So in order to do 5 and 6, we have to go to the D shells. We have to go to the D subshells because that's the only way we can have 5 or 6. And what that means is in the chart we'd have to be at least in row 3. So we'd be in the row with sulfur and phosphorus and all of that. So just keep that in mind. So when we're doing the next two, we'll be in the 3rd row of the chart or lower. And also, we're not going to really be worrying about the things in the 1st row or the 2nd row. In other words, when we do the next two, we're going to forget about the 1s2 and the 2s2 and the 2p whatever, the 2p6 or whatever, because they're not valence now. We're now in the 3rd row. Okay, so let's go to the next slide. Oh, and here's another picture of the SP. So let's go to the next slide. And then this is a summary. So we've already talked about this kind of like a lot, so let's go to the next slide. All right, so what you call, if you have 5 charge clouds, is DSP3, which is sometimes also called SP3D. It's the same thing. So add up the exponents, D1S1P3, right? 1 plus 1 plus 3, that's 5 charge clouds, so it's trigonal bipyramidal for the electronic geometry. Next slide. Okay, so this would be a good exercise for you. So draw the Lewis dot structure for PCl5. So if you haven't already done it, I would do that. And what's going to happen is that in this case, chlorine has 7 valence electrons, so I'll just very quickly run through this. 5 times 7 is 35, plus the 5 for the phosphorus would be 40. So you put the P in the middle with 5 chlorines around it, and you would use 10 of those 40 electrons to do those bonds, and that leaves 30. So now start putting them on the chlorines, right? You can put 6 on each of the chlorines, and you've got 5 of them, so 5 times 6 is 30, so that means when you put 6 electrons on each of the chlorines, you've used all your electrons. So the phosphorus is going to have only 5 things around it, so the shape would be trigonal bipyramidal. Next slide. And the bond angles, I haven't really worried about that much because you can just look at it and see what they are. It's either going to, almost always either going to be 90 degrees or 120 degrees or 180 degrees, and you can just see that. The only exception is for tetrahedral. You have to remember that tetrahedral has bond angles of 109.5. Next slide. Okay, next slide. Next slide. Next. 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 Okay, so here's a picture of PCl5. The thing in the middle that's orange is the phosphorus, and the 5 green things around in the outside are the chlorines. So this is trigonal bipyramidal. So the question is, how would this happen? So remember that for sp2 we had 1s and we had 2p. We had 3p, sorry, and we hybridized those to make 2 of those p's came down to make 3 sp hybrid orbitals, sp2 hybrid orbitals, sorry. And one of them stayed as a p electron up at the top. So let's see how this could happen where we want to wind up with 5. So next slide. And let's just go to the next slide because it's easier for you to see. All right, so look, first of all, notice that we're in the third row. So we have, for phosphorus, normally in its ground state would be 3s2, 3p3. So it would be the same as nitrogen, except nitrogen would be 2s2, 2p3. So P's in the row below it. So how can we get that? So the way it is right there, there's no way it would make 5 equivalent orbitals, right? It would make 2 for the S's and 3 for the P's, which wouldn't work. So somehow we have to get those 5 electrons so that they're all the same in energy. So in this case, we leave the P1s alone and we move one of the S's up to the 3D. Now those 3Ds were originally empty, but now we're going to take one of the 3s electrons and migrate it all the way over to the 3D to that first vacant 3D orbital. When we do that, we now have 1 electron in 3s, 3 in 3p, and 1 in 3d. And then what we would have to do is we would have to lower the 3d, and then the 3p's could probably stay about where they are. They might have to go up a little bit, and then the 1 in the 3s would have to come up quite a bit. So that what we would have then would be 5 orbitals that are exactly the same in energy. And we call all 5 of those dsp3 orbitals, or dsp3 hybrid orbitals. And then at the bottom there, it's showing what it would look like if you had 5 bonds to the chlorines, to the 5 chlorines. You would then have 1 chlorine contributing 1 electron to each one of those 5 squares that we had in the second middle row there. So one, like the one on the left, from 1 chlorine, and then the 3 in the middle from 3 other chlorines. And so the chlorines each have 7 electrons, so they'll donate 1 of those to each of these to make a bond, and they'll keep the other 6, and they'll be arranged as 3 lone pairs. So that's what it would look like at the end stage when you have the PCl5, the bottom there. Next slide. Excuse me. All right, so here's what it would look like in picture form. So the P is in the middle. It has 5 hybrid dsp3 orbitals. Again, D1, S1, P3, 1 plus 1 plus 3 is 5. So you want 5 things oriented around the central atom, 1, 2, 3, 4, 5 chlorines. So each of those bonds between the P and the Cl's will be a sigma bond because the bonds are all going directly between the 2 nuclei. And it doesn't matter that these are like hybrid orbitals that are making these sigma bonds. They're still sigma bonds. Okay, so that's your example there for dsp3, and we're almost finished. Next slide. This is the last one. Okay, so D2sp3 is just like what we just saw, except we're going to move 2 electrons up to the D subshell. So next slide. So let's just skip this because I don't want this to go more than like an hour and 15 minutes if possible. So let's go to the next slide. So next slide. And next. And next. There. Okay, so this is what SF6 would look like. Notice there's no lone pairs there. So you have 6 fluorines arranged around a central atom, which is S. All right, so to get this kind of a shape, which is an octahedral shape, you have to have, remember that when we were doing octahedral at the very beginning for the VSEPR portion, we said that you have to have 6 things arranged around a central atom, and that's what we see here. But to get to this, you have to use the d orbitals, and you have to use 2 electrons in 2 different d orbitals, 1 electron in an s orbital, and 3 electrons in p orbitals, and that's how you actually get this. So next slide. Oh, and also before we go on, how many electrons are arranged around that s? Well, count them: 2, 4, 6, 8, 10, 12. Again, so why is that possible for s? So think about that. Next slide. Next. So here we see a picture that's just like the one that we saw before. for dsp3, we're starting off with two 3s electrons, and then this time in the p shells, we have 4 electrons. We have 1, 2, 3 pointing up and 1 pointing down, none in the 3d at the ground state. So to get the D2 sp3 hybridization, move one of the s electrons, bump it up to the empty 3d, the first one, and then take that electron that's pointing down in the 3p, the first 3p orbital, and bump it up to the 3d orbital that would be the second one. So now notice we have 1 in the 3s, 3 in the 3p, and 2 in the 3d. So 1 plus 3 plus 2 is 6, which means that can make 6 bonds when it's in that state. So when you do it like is shown in B there, that's called D2sp3 hybridization. And it can make 6 bonds as we saw in the previous slides. So when it does that, that's going to be shown in part C at the bottom. Each of the F's also, like the one we saw before with the chlorines, has 7 valence electrons. So it will donate one of those and keep 6 as lone pairs, 3 lone pairs. The one that it donates in all of those is shown as being pointing down, an arrow that's pointing down. And so each one of those has 2 electrons, and they're all bonds. They're all sigma bonds. Next slide. Okay, so we finished up with valence bond. Let's just talk for just a few moments about molecular orbital theory. Next slide. Let's go to the next slide. All right, let's just go through just a bit of this. When we use molecular orbital theory, we're doing this completely differently because we're not drawing a picture of what it looks like. We're drawing a chart that shows where the electrons are going. So we're actually using a diagram. So the way the diagrams are constructed is you're going to be showing how a bond forms. So you put one atom on the left and the other atom on the right, and then when they form a bond to make a molecule, you put that part in the middle. So the thing on the left and the right are called atomic orbitals, and the thing in the middle is called the molecular orbital. Now you can have both. So you'll either have the 2 atoms with their electrons there, or you'll have the thing in the middle where the electrons have been moved into molecular orbitals. Okay, next slide. So don't worry about this. If you don't understand this, you really don't need to. But quantum mechanics predicts that when 2 atomic orbitals approach each other, like 2 H atoms, then they can either go down in energy if they're in phase, and that would be a bonding orbital, and that's what usually happens. But sometimes if you have too many electrons in there to fit into one orbital, in other words, if you have more than 2 electrons, like for example, if you have an H and an H minus, where you've got 2 electrons on one H, then you've got too many electrons. So one of them will have to go into a different orbital, and that one is going to be higher in energy than they would have been just if they'd been separated. And that's called an anti-bonding orbital. Again, so don't worry too much about this. If you don't get it, just look at the pictures when we get to them. Next slide. Next slide. So here is a picture. So we've got these 2 hydrogens that are approaching each other. When they come together, notice that one arrow is pointing down to the right, so that's the bonding orbital, and it's lower in energy than the atoms would have been separated. And then there's one pointing up to the right, and that's the anti-bonding orbital, and there isn't a bond formed there at all. It's just a place where the extra electrons can go that are too many electrons to go into the bond below that. So anytime you have, like, for example, if you have H minus plus H, or if you have H plus HE, or if you have HE plus HE, you're going to have too many electrons to fit in the bonding orbital. Remember, you can only put 2 electrons in any orbital. So when that happens, they have to go somewhere. So the extra ones that are left over, which there can either be 1 or 2, will have to go up to the top orbital, which is an anti-bonding orbital. Okay, this is not a particularly stable thing, and it isn't even a bond. They're just kind of like being stuck up there for storage. All right, so for example, if you had two heliums, then you would have two electrons on each. So when you bring them together and try to make a bond, you can't, because you've got four electrons. Two will go to the bottom and two will go to the top. And so the two on the top kind of like negate the one on the bottom, the two on the bottom, depending on whether you're talking about bonds or electrons. So you don't actually have a bond. So what happens is if you try to make a bond between helium and another helium, it won't work. Next slide. Oh, crap. I accidentally clicked 2. I'm sorry. So, all right, anyway, here's another picture of it. If you have two things that come together, two s orbitals and two atoms, they'll make a bonding orbital. But if you have too many electrons, they'll go up to the anti-bonding orbital that is above there. And they're always present, although, if you look at the lecture notes, I gave you a whole bunch of more advanced stuff on this. And when you get into the more advanced molecules, if you want to just glance at it, you'll see that some of the more advanced diagrams don't show anti-bonding orbitals for everything. But for your purposes, you can pretty much just consider that all of the bonding orbitals will have a corresponding anti-bonding orbital. Next slide. All right, next slide. So here we go. Here's a picture, and this is what you'll have to do on the test. And it's really super easy. So here what we have is two hydrogen atoms that are coming together to make H2. So if you look at the left-hand side, that's what I really want to talk about. That's a molecular orbital diagram. And so if you look on the left and on the right of that diagram, you've got one line. And you see HA above the first one on the left. The A just stands for the first hydrogen atom. You could have also called it H1. But they didn't because it would be confusing. And then the one on the right they call HB. So look below that HB and you see another atomic orbital. Notice it's in the middle in terms of its energy between the two that are in the middle of the diagram. All right, so the way that you do these basically is you count the number of electrons and just stick them in the diagram, and the diagram will always be provided for you. So just put them in there. So how many electrons do you have? Well, on the left you have 1, on the right you have 1, so you have a total of 2. So just play like you're making an H2 molecule, remove the arrow on the left and the right and put them in the diagram in the middle, and you have 2, so you can put both of them in that bottom bonding orbital. So that's referred to as sigma 1, and it would be called sigma 1s but usually they'll just call it sigma 1. But it's sigma 1s because it's coming from s atomic orbitals. So when they're on the atoms, we call it 1s. When it's in the molecule, we call it sigma 1s. Okay, so just pretend for a minute that you have, on the left, instead of having 1 arrow, you have 2. Well, to do this same thing we just did, just add 2 plus 1, you would have 3 electrons in that case. So start putting them into the diagram in the middle. Well, you can only put 2 of them in the bottom one. So where does that third one have to go? Okay, so think about it for a minute. Let's go on to the next slide. Next. Oh, gosh. I did it again. Okay, but happily, this is the same thing that was on the previous slide. All right, so here, this is what would happen if we had 3 instead of 2. In other words, if that atom on the left were H minus instead of H, then you would have 2 electrons for it and 1 for the H that's on the right. So when you start to put them into the diagram in the middle, you would only be able to put 2 at the bottom, and you'd have to put the third one up at the top because there's nowhere else for it to go. Okay, so when you have a situation like that, it's not as stable, obviously, as it would be if you just had 2 electrons. If you have 2 electrons and they're both in a bonding orbital, then that would be stable. But in this case, it won't be as stable. The reason is because when you put one of the electrons up top there in the anti-bonding orbital, it destabilizes the molecule. So what we can do is we can figure out a bond order for these, and that will tell us what kind of bond it is. For example, if we do the bond order calculation for H2 and we see that it's 1, that means it's a single bond. Let's do it for this one. Now remember, for H2 it would have only been the 2 things in the bottom. So the way you do the calculation is you subtract the ones that are in the number of electrons in anti-bonding orbitals, which are marked with an asterisk, and you subtract those from the bonding electrons. So in this case, you would be subtracting 1 electron from 2 electrons, 1 in the top and 2 in the bottom. So what's 2 minus 1? It's 1. And then you always end it by dividing by 2. Always. So in this case, it would be 2 minus 1 is 1, and 1 divided by 2 is a half. In other words, this is a 1/2 bond. It's a 1/2 bond. So it's less strong than a single bond. Now, let's just use our imagination. What if you didn't have that third electron up in the top anti-bonding orbital? Well, then you would have 2 in the bonding minus 0 in the top. So 2 minus 0 would be 2. Divided by 2 would be 1. 2 divided by 2 is 1. Single bond. So that would be the normal situation when you have an H and another H that make a bond. They make a single bond. Okay, this is the other thing that you'll have to do on the tests. You'll have to figure out the bond orders. And that will basically be mainly it. They may ask one other thing, which I'll mention in a moment, but basically that's what you'll have to do. So all you have to do is count the number of electrons on the left and add that to the number of electrons or arrows on the right. So in this case, you've got 3, and then just start at the very bottom and start putting them in 2 at a time. Up, down, and okay, that's complicated a little bit when we'll get to the p orbitals in just a moment, but basically that's what you want to do, is you just want to put them in 2 in each orbital, and then just start from the bottom and work your way up. And then they'll almost always ask you to find the bond order. So here it would be 2 minus 1 is 1, 1 divided by 2 is 1/2. Next slide. Here's what we would have if we had 2 H's only. So we would have 1 electron in the H on the right, 1 in the H on the left. So that's 2. So 1, 2. So start filling from the bottom. You can put 2 in each orbital. So put 2 in the bottom, and that's all you have. So you're done. To get the bond order, it's 2, which is the number in the bottom one, minus 0, which is the number in the top. 2 minus 0 is 2, and then 2 divided by 2 is 1. It's a single bond. So again, while we're looking at this, and we kind of already understand this hopefully, again, look at that diagram. You either will have the situation with the 2 green orbitals, or you'll have the situation with the blue and the red orbitals. You won't have both at the same time. They'll show both of them, but they're not going to both exist simultaneously because they can't. It's either going to be 2 atoms or it's going to be 1 H2 molecule. Next slide. All right, so what happens if we have H2 minus? Well, we've already discussed this. We'd have 3 electrons instead of 2. So we start putting 3 electrons into the MO diagram in the middle, but we can only put 2 in the bottom, so we have to put 1 in the top. We've already talked about this. So the bond order would be 2 minus 1 is 1, and 1 divided by 2 is a half. So it's a very weak bond. What about He2? We've also talked about this one, right? So the green orbitals have 2 electrons each for the 2 heliums. This time it's heliums instead of hydrogens. That isn't shown, but that's what it is. It would have to be. So 2 plus 2 is 4. So we got 4 electrons. We want to start putting them in from the bottom, 2 in each orbital. So 2 can go on the bottom, but we still have 2 left over. They have to go on the top. So the bond order here would be 2 minus 2, which is 0, and then 0 divided by 2 is 0. So the bond order is 0. In other words, you don't have a bond. And that makes sense because helium doesn't want a bond. It wants to stay by itself because it's a noble gas. Next slide. All right, this is the third thing that they could ask. And this one will require you to remember the difference between what they mean when they say diamagnetic and paramagnetic. So what you can try to do if you want to make this easy for yourself is try to remember that dia means through. Through. Dia means through. If you can remember that, you can remember the definitions. Because that means that if it's diamagnetic, it will go right through a magnetic field. And the reason is because all the electrons are paired. So there isn't any kind of an electronic magnetic or magnetic moment that's out there that's going to attract it to either the positive or negative pole of the magnet. So dia means through, so that means that diamagnetic things will go through a magnetic field. Para is just the opposite, but you don't really have to remember it because you know that if the dia is the one that goes through, then the para is the one that doesn't go through. In other words, it's the one that does get attracted. And what it means is that there's at least one electron in there that is not paired up with another electron. So that electronic magnetic moment is going to create a little bit of a magnetic field around that electron that will be attracted to the magnet. And one of the reasons why MO theory is powerful is because it allows us to see why O2 is actually paramagnetic when it's shown that it should be diamagnetic by all the other theories, by the Lewis dot structure and the VSEPR and all that. They all would indicate that it should be diamagnetic. In other words, it should go right through the magnetic field, but it doesn't. So let's go to the next slide. So p orbitals, next slide. So these get a little bit more complicated. So the reason is because when you get to p orbitals, you have two different kinds of p orbitals. The ones that are pointing right at each other, which are going to make sigma bonds, so we have to treat those separately from the other two, which are pointing either up and down or left and right. So those are going to be called pi 2p orbitals, and the ones that point right at each other are called sigma 2p. So even though they're p orbitals, they can still make sigma bonds, which we already knew that. Let's go to the next slide. So you can see here these diagrams are just a little more complicated because we've got, in addition to the two things at the bottom, we've got 1, 2, 3, 4 at the top. So let's just look at this real quickly. Notice also that we're in the second row. So we're going to start now with 2s and 2p, not 1s. 1s is still down there, but we just don't care about it because it's not valence. So look at N2 at the left. The thing on the left is N2, and the things on the right would be for either O2 or F2. And the reason they're dividing them like this is because they're different. And that's just the way they happen in nature. So again, let's just do the N2. So if you're given N2, what you would do is you would take N, count the valence electrons. Well, it's in the fifth column, so it has 5 valence electrons. But there's 2 of them, so that means you're going to deal with 10 total electrons. So just start at the bottom and go 2, 4, 6, 8, 10. So you're going to fill up the blue, the red, and then the 3 blues. They're all going to be full. Just notice that when you get to the pi things there's 2 of them, right? So come up to the 1, 2, 3 from the bottom. There's 2 pi 2p orbitals. So remember, you have to use Hund's rule there, even though here it wouldn't really make a difference, but it will for O. So when you get to those, you have to put in 1 spin up, and then go to the other one and put it in spin up, and then go back to the first one and put in spin down, and then the second one spin down. So for nitrogen, if we do what I just said, we put in 2, 4, 6, 8, 10, everything is going to be full up to that blue line that says sigma 2p. So if we do the bond order for that, it's easy to see it here because they've got it color-coded. So we want to just count how many electrons are in the blue line orbitals and subtract the red ones. So how many are in the blues? Well, 2, 4, 6, 8. And then how many are in the red? 2. So again, starting from the bottom, there's 2 in the sigma 2s. There's 4 in the pi 2p because there's 2 of them, and 2 in the sigma 2p. For a total of 8, that's 8 bonding minus 2 anti-bonding. So 8 minus 2 is 6. 6 divided by 2 is 3. It's telling you that N2 has a triple bond. Okay, now if you look over to the right for O2 and F2, Let's do F2. Oh, and before we do that, I'm sorry. Look back at N2 for just a moment. Notice all of those electrons are paired. So what that means is if all the electrons are paired, N2 will go right through a magnetic field and it won't be attracted to the magnets because there's no electric or magnetic moment on the electrons to attract it. So it will be diamagnetic. All right, so look, the three things that they'll basically ask would be exactly what we just did. For N2, for example, I mean, they wouldn't have to ask N2, but count the number of valence electrons in N. Well, you probably already know by now it's 5, but you have one on the left and one on the right, so 5 plus 5 is 10. So that means we need to take 10 electrons and fill up that chart from the bottom up, putting 2 in each one. And in this one, it doesn't really matter that you've got 2 for the pi 2p's, but it will for the O. But just put in 2, 4, 6, 8, 10, and then you're done with the first part. That's all you have to do. And so I don't really get why this is so hard for students to do this, because, I mean, maybe the theory behind it is difficult, but you don't have to know the theory. You just have to be able to count to 10 and then go 2, 4, 6, 8, 10. So anyway, and then the next thing would be to find the bond order. So it would be 2, 4, 6, 8 minus 2, which would be 6, and then 6 divided by 2, which would be 3. So the bond order would be 3, and then would it be diamagnetic or paramagnetic? Just look, are all the electrons paired? Yes, so it would be dia. Remember, dia means through, so it will go through the electric field because all the electrons in all those orbitals are paired. And if you don't see that, just like copy this down on a piece of paper and then fill it out, and you'll see what I'm talking about. Okay, so if we do F2 over on the right-hand side, it's going to be the same as N2, except you're going to go further up. So you would have 14 instead of 10. That's the only difference. So starting at the bottom, 2 in the blue, 2 in the red, 2 in the blue, and then you're supposed to go 1, 1, 2, 2 for that next one for the pi 2p, but in this case, it doesn't matter in this case because you're going to go past it. So 2, 4, 6, 8, 10, 12, 14 means you're going to fill up all but that very top red line. And then to get the bond order, you've got, in the blue ones, you've got 2, 4, 6, 8, and in the red ones, you've got 6. So 8 minus 6 is 2, 2 divided by 2 is 1. So the bond order for F2 is 1, and it's, again, diamagnetic because everything is paired. Now, we use that same chart we just used on the right-hand side. We use it also for O. So, but O only has 6 valence electrons and not 7, so 6 and 6 is 12. So start from the bottom and put in 2, 4, 6, 8, 10, 12, but we have a problem when we get to the 11th and 12th one. So again, the blue would be 2 at the bottom, then the 2s, sigma 2s, sigma star 2s, 2, sigma 2p, 2, and then both of the pi 2p's 2. But we have 2 more left over that have to go into the pi star 2p's. We only have 2 though, so one has to go spin up in the first one on the left, and one has to go spin up in the one on the right. They're not paired. So that means that this is not diamagnetic, it's paramagnetic. So if you try to shoot O2 through a magnet, it won't go. It will attract to either of the poles on either side, and it will eventually solidify and make like kind of something that looks like ice. It's liquid oxygen. And there's a picture of that in your lecture notes that I didn't transfer over. All right, what would the bond order be? Well, it would be 2, 4, 6, 8 in the blues minus 2, 4 in the reds. So 8 minus 4 is 4. 4 divided by 2 is 2. So O2 has a double bond. F2 has a single bond. N2 has a triple bond. Okay, that's absolutely all you need to know for this section. It isn't that much. So just count the total number of electrons, put them in starting at the bottom, 2 in each orbital, then find the bond order by subtracting the blue ones minus the red ones. If they're not color-coded, you just want the ones that don't have the asterisks minus the ones that do, and then divide by 2. And then the third thing would be just to look to see if all the electrons are all paired. If they're not, then it's going to be paramagnetic. If they are, it's dia. It'll go through the magnetic field. Next slide. And you can see here the answers for these. So O2, you see those two arrows at the top that are not paired. That makes it paramagnetic. And again, molecular orbital theory is the only theory that we've studied that actually would have predicted that. And then the bond order. So the bond order for F2 is 1, O2 is 2, N2 is 3. Next slide. And here's another one that includes boron and carbon. If you want to look at it, it might be good practice for the test. I'm not saying it's going to be on the test, but it might be on the final. So it's what you would get if you did for B2 and C2, and those both have the same kind of a diagram that N2 has. And the reason that O2 and F2 are different is because of the order. If you look there for the B, C, and N, you've got the pi 2p is below the sigma 2p. So this would be like the 1, 2, 3, and 4 rows from the bottom. For O2 and F2, it's the reverse. Next slide. And then the only thing we have left, and we're going to wrap this up, I think I've already gone a little long. For benzene, benzene is 6 carbons that are all in a circle, and they all have a double bond. So this is what the sigma bonds would look like, and each of them are also bonded to an H. But let's go to the next slide. This is what the pi bonds would look like. So we've got those p electrons that are sticking up and down on all 6 of the carbons, and so they'll make 6 pi bonds, but really what you wind up with is what looks like the thing on the right. It is just where the electrons are basically free, like they would be in a metal, to just move around and around that circle. And when you have a situation like that, it's called resonance. It will be a situation where you have 2 structures that are equivalent. And what that would refer to here in benzene would be that the double bonds could either between 1 and 2, and 3 and 4, and 5 and 6, or they could be between 1 and 6, 5 and 4, and 3 and 2. And it sounds like I just said the same thing, but I actually didn't. So you'd actually have to draw that out to see that. But anyway, let's wrap this up because we're already, I think, long. So I'll see you in the next chapter.